I'm making this video to help you better understand how to prepare for the quiz using the Excel singularity spreadsheet. So we had talked about how we had a shaft that is simply supported. So I know I have a reaction on one end, RA, and a reaction on the other end, RB, that prevents deflection but does not prevent rotation. So you know that I have a coordinate system that I am going to attach to this shaft, an XY coordinate system as so, and we are going to measure RA as the 0 point. All right, so now we want to apply some loads to this. I'm not going to worry about applying distributed loads. I'm just going to say I got F1 over at X1, F2 at X2. I'm going to make my life simple so that we don't have to spend too much time on this. So now what we have to do is we want to describe the moment as a function of X. So the moment as a function of X is going to be equal to RA times X minus F1 times X minus x1 to the first power. So this is the singularity function. And the minus f1 means that it's pointing in the negative y direction. We subtract from that f2 at x minus x2 to the first power. And that's the end of it. If we only had two forces acting, we have those two forces with the singularity functions that tell us when to turn those forces on. So right off the bat, we know something. We know that at L, m at x equal to L has got to be equal to 0. So what does that say? It says that RA times L is equal to F1 times, now it becomes regular, L minus X1. These are now regular brackets because we are past the point of application of the load 1. We're on the right side of the beam, all the way over at reaction B is where we're doing this. And I have to add to that F2 times L minus X2. That is simply sum of the moment. That's all it is. So we can solve for RA from that equation. It's just 1 over L times the quantity F1 L minus X1 plus F2 L minus X2. We actually know what that is. If we know the dimension L, we know the forces, we know where the forces are applied, then we have just solved for RA. Next thing we do is sum of the forces in the y direction being equal to 0 allows us to solve for RB. So reaction A and reaction B, easy to solve for. We've taken care of that. Next thing we need to do is write the deflection equation where d squared y dx squared is equal to 1 over EI times the moment which varies as a function of x. Now, we don't even have to go there yet, but we know we're going to have to integrate this twice. So we will get two integration constants. We'll come back to that in a moment. But first, I will go back to this moment expression up here. I will plug RA into it, and that allows us to sort out what the moment is and write the moment as a function of x. So we have the moment as a function of x. We put that into our spreadsheet. We solve for RA. That gives us a perfectly good expression for the moment as a function of x. That means we could find the max moment. All we have to do is sort through our spreadsheet using the max function, and it will pull out the maximum moment for us. So that's relatively straightforward. Why do we care about the max moment? Because the bending stress, maximum value of the bending stress, is going to be my over I, where if we have a circular shaft of diameter d, then y is d over 2, and I is pi d to the fourth over 64. Those are things that we know. So I'm going to go ahead and plug in. I'm going to say my bending stress is just equal to my maximum bending stress is equal to my max moment times d over 2 divided by pi d to the fourth over 64. That gives me 32m over pi d cubed. So there's my maximum bending stress. Now, this allows me to compute a first guess shaft diameter because I can take this maximum stress and relate it to my yield strength. If I am given a design factor of safety, well, what is the design factor of safety? It's just the yield strength over the allowable stress. Well, the maximum allowable stress would be given by this moment equation right up here, where we calculate the maximum allowable stress is given by this equation right up here. So what that means is that the allowable max, which is 32 m max, which you can find from your spreadsheet, divided by pi d cubed. That's equal to my yield strength divided by my design factor of safety. That gives us our target first estimate for the diameter of the shaft that is required for a uniform, solid, circular shaft exposed to the loading that we just said is going to be applied to that shaft. So what do we need to know? We must know SY. What are we making it out of? We got to look that up for the given alloy. Usually these are 1018 steels. So it's easy for us to find that. The other thing that we need to know is the design factor of safety. With that, you can easily calculate a target diameter for your shaft. That allows you to select shafts. Now that I have that target diameter, I can calculate I, because I is just pi d to the fourth over 64. Now I can go back to my deflection equation, which is 1 over EI times my moment equation, and I'll just write that out. We have my moment equation is RA times X minus F1 times X minus X1 to the first power minus F2 times X minus X2 to the first power. So I'm going to go ahead and integrate that. I get that my slope dy dx is 1 over EI times the quantity RA x squared over 2 minus 1/2 F1 x minus x1 squared minus 1/2 F2 x minus x2 squared plus C1. And I've decided to put my C1 inside the brackets, meaning I'm multiplying all four of these terms by 1 over EI. We integrate again. Y equals 1 over EI times the quantity. 1/2 RA, well, multiplied by 3, you get 1/6 RA x cubed minus 1/6 F1 x minus x1 cubed minus 1/6 F2 x minus x2 cubed plus C1x plus C2. What we know is this. We know that at x equal to 0, y equal to 0, and all of these terms are 0 at x equal to 0. So this implies that C2 must be equal to 0. At x equal to L, y is also equal to 0. These are the simple support conditions at A and at B. A is at x equal to 0, B is at x equal to L. From this, we now solve for C1. How do we do that? Well, we set y equal to 0, multiply through by EI, and we get that C1 times L is going to be equal to minus 1/6 RA L cubed plus 1/6 F1 L minus X1 cubed. Normal brackets now. Plus 1/6 F2 L minus X2 cubed. That's all we have. We divide through by L. We find that C1 is minus 1/6 RA L squared plus F1 over 6L, L minus X1 cubed plus F2 over 6L, L minus X2 cubed. We can solve for C1. Once we have C1, we plug it back into the equation up here for the deflection, and we now have a completely solved equation for the deflection as a function of position along the shaft.